Welcome everyone to today's webinar titled Gas Flow Measurement in Cement Plants, Improving Tertiary Air Control, Downcomer Flow, and Pyroprocess Optimization. My name is Ravi Krishnan, Managing Director, Krishnan & Associates, and today's discussion focuses on a challenge that exists in nearly every cement plant: understanding and controlling gas flows throughout the pyro process. While flow measurement may seem like a narrow topic, it directly impacts kiln stability, combustion efficiency, NOx emissions, fan power consumption, clinker quality, and overall plant performance. We have an excellent panel today, and I will have each of them provide a brief introduction. So let's start first with Alexandra Graf from PROMECON.
Hello, thank you, Ravi. So welcome on board. Welcome at our today's session. So I'm very happy. My name is Alexandra Graf, or shortly Alexa. I'm very happy to have this presentation with excellent panels. I'm with 10 years now with process engineering, and some of you I already met at some conferences. And today we want to discuss about gas flow data and how it's influencing us. So thank you for this. And if there is any question, some know me from LinkedIn. I think this is enough. Thank you.
Thanks, Alexa. Next, we have Xavier Dubert from XDH Consulting.
Hello, everybody. I have 30 plus years in clinker and cement operations and industry, both in Europe and North America, with focus on fuels, pyroprocessing, air pollution control, and anything that has to do with production stabilization and energy usage reductions target.
Brilliant. Our next panelist we have is Jean-Philippe Gravel from Cement, Quebec.
Yeah, good morning, everyone, or good afternoon, or good evening, depending from where you are in the world. So yes, I'm Jean-Philippe Gravel, or shortly just JP. You could just call me JP during the presentation. So I'm a chemical engineer with a bachelor and a master degree in chemical engineering, with a specialization in gas solid reaction. So I bring also experience across advanced research and industrial process engineering, including 12 years in electrochemistry, corrosion, and material performance with the Government of Canada and the pipeline industry in Calgary, Alberta, in Canada. I later transitioned to the cement industry as a process engineer at Cement Quebec. It's located close to Quebec City, where I focus on pyroprocess operation and optimization, including the kiln, the burner. I successfully lead the upgrade actually at our burner here at the cement plant. And I work also on the preheater, and we have a hot disk also. So that's it. Thank you.
Thank you. Then we have Matthias Schumacher from AIX Process.
Thank you, Ravi, and hello, everyone. So my name is, as said, Matthias Schumacher. I don't have a nickname. My background is process engineer. I'm working at X Process as the director of our cement technology department. X Process, some of you may not know it, is offering process optimization engineering, which is based on advanced CFD modeling. Myself, I have 20 years experience in cement process optimization worldwide, and I have conducted more than 300 cement plant optimization projects on different topics. My focus is on optimization of the pyro process and on alternative fuel combustion. And for a few recent years, I'm also the product owner of Kiln Expert, which is the AI-based pyro process controller of X Process.
Excellent. And our final panelist, John Kline from Kline Consulting.
Hello, everybody. I've been in the industry over 50 years now. Most notably, I spent 21 years in various international executive positions with Lafarge while it was still a company. I've been consulting since retirement in 2012. My focus has been on decarbonization, digitalization, and optimization of cement plants, along with training.
Brilliant. So let's move on and let Alexa will begin by setting the stage with an overview of continuous gas flow measurement, challenges and solutions. And following her introduction, we will move into an interactive discussion with our panelists. So over to you, Alexa.
Thank you, Ravi. So also from me, a warm welcome to everyone. Good morning, good afternoon, depending. I also see some registrations from New Zealand, so welcome at night. And welcome from PROMECON in Germany. I'm proud and honored that we have more than 180 cement professionals, mainly pyroprocess engineers here within this Fireside Chat, who registered from all over the world. To me, this shows one thing: reliable process data and gas flow has become one of the hottest topics in our industry, same like digitalization and AI, which I will cover today a bit. Because reliability is often overlooked. Yeah. So today, when everybody is talking on conference about artificial intelligence, expert systems, process excellence, robots, digitalization, the reliability is the foundation, and it's actually more relevant than ever. Yes. So please let us start some discussion because before we discuss AI, let us first slow down to speed up. I like to say this a lot because when you have some process optimization, the first step is to slow down, and then you can check your data, and then you can speed up. So let me ask you 3 simple questions. Do you know your real tertiary airflow? Do you know your actual secondary air to tertiary air split? And last but not least, do you know how much fan energy you could save by knowing your real-time fuel to air ratio? If not, then you're completely right here in this session, and we have to talk. Why are you joining conferences and panels and discussions and talking about AI? I'm really interested in all these questions, and for sure the answers even more, because before implementing a control system or automation or a closed loop system, or even an AI that predicts you some build-ups or process malfunction, our first job as an engineer is always to check the quality of the process data. So reliable process data is the foundation, and without this reliable, low maintenance sensors, digitalization will not work. We all know the challenges from our daily operation and plant audits. So we have high dust concentrations, we have heat, manual measurements, drifting differential pressure devices, unstable readings. During my discussion with operators, they ask me questions how they benefit from data when they are not trusting them. So how should they implement it to the DCS system, for example? And the common statement is, I prefer to rely on my manual judgment, my long-term experience. I'm doing my settings myself rather than I'm using an unreliable reading for my kiln operation. And I fully understand them because they take care of a 24/7 process, which should never fail, where a process or a kiln shutdown is the worst case scenario. So they take care of this, and that's why they want to have it as stable as possible. And reliability is there the key. So I'm convinced that only reliable drift-free process data can become the foundation for this digitalization, closed loops, or even in future some AI application for the milling or the grinding or even for the pyro process. A few months ago, I had the opportunity to visit CEMEX in Miami. during the IEEE conference. May was also there, and the plant manager Alberto showed us some self-developed AI tool, which is an assistant called Mike. And he explained that he can now ask during his night breakfast or even on holidays or vacation, he can ask, hey Mike, how are mills 5 and 6 performing today? Do we need to act? Is there anything to do? And within seconds, the system answered him which mill was operating normally, which one is out of spec, which one we can hold back, let's call it this way, or which action we have to do so that we are not 10% out of spec, for example. And all of the attendees found this and very fascinating. But then not only me, but many people ask ourselves, how can the AI tool know that? Yes, how is it really working? And the answer is very simple, because somebody validated and checked and measured the process in the first step, and then there is for sure some prediction and so on. So AI is only as good as the data receives. It receives data from temperature meter, vibration, especially for the milling section, some clinker throughput, some gas flow data for sure. So that is exactly what I'm so proud today to have such an experienced panel of experts, which I'm having a lot of discussions about this. So with John Kline, he introduced himself, so we all know him. Jean-Philippe, which is having reliable flow meters from PROMECON at the preheater tower, at coal mill, and also Tertiary, and we will all cover these installations today and discuss about the benefits of it. And Xavier is very valuable for all the alternative fuel topics, and Matthias has introduced his role as the product owner for this kiln expert. And all of these guys which I discussed, we have discussions about one common topic: reliable gas flow data. May I repeat it now in this intro? Too often the word reliability, but it's so key. So today we will hear some practical examples. So how tertiary air measurement helps you to identify material build-ups, maybe at your preheater venturi, how increasing gas velocity indicates a shrinking of the tertiary air duct, even while the damper position is unchanged. But so you assume that everything is fine, but there is some change in the process. Or how the TA flow data gives you information about damper aging, refractory wear throughout your campaign. We can also discuss how especially the tertiary air can optimize your rotary kiln and the pre-combustion chamber for this alternative fuel burning, how this is balanced, because we all discuss about mass and heat balance, about the value out of having the gas flow data, because having a gas flow meter is for sure the first step, but you need to implement it to the process to get some value, yes. And last but not least, we will also cover the real-time gas flow data for the fan operation instead of relying on theoretically fan curves, yes. So we will discuss how reliable process data supports your alternative fuel rates, your lower energy consumptions, and making you a more stable pyro process. The best part of today, I'm very proud of this, is that it's not this classical presentation, no slides. It's a pure discussion, and you're very welcome. So it's your opportunity to ask questions directly to some of the world's leading cement experts. I'm very proud that we have this excellent panel. So please challenge them. Today you can ask, and maybe tomorrow you can fix a problem in your plant, or at least discuss this with your team. And use the experience of today. Even if you have questions, use this chat and we will handle all this. So let's explore in a way how human intelligence, from our experts and reliable gas flow data together can unlock the full potential of AI and digitalization in the cement production. Thank you.
Thank you very much, Alexa, for that excellent setting the stage. And so it's time to commence our panel discussion. So our first section is going to talk about why flow measurement matters. So my first question is to John Kline. John has spent decades operating and improving cement plants globally. So let me ask you this question. How important is accurate gas flow?
So as Alexandra alluded to, we're on the cusp now of seeing the AI implementation. At the same time, many of us are under pressure to reduce our carbon footprints. So we're looking to use AI to optimize, standardize our operations, improve our product quality, but we're also going to have to change just about everything we do, our fuels, maybe our back-end processes, or maybe we're going to oxy-fuel combustion, etc. So we're going to have to make a bunch of changes for the decarbonization. At the same time, we're trying to get assistance from AI. So to make all of this work, we need to have good, accurate information. And accurate, consistent can be wrong as long as it's consistently wrong, but more precise, more accurate, the better. And that's what's going to enable us to, I think, transform from our current operations into these future AI-assisted low-carbon operations.
You're absolutely right, John. Just let me ask, if you had to prioritize an area where poor flow visibility causes the most operational pain, let me know, where would it be?
Well, what the objective of every plan is to produce a very reactive clinker. Reactive clinker, that's basically the fundamental part of our product. So that means getting the right heat profile in the kiln, the right heat transfer into the clinker, not too much, not too little. And most plants these days are using pre-calciners. So we have combustion in two spots. We need the combustion to drive the reactions that we need. If you have combustion, you need airflow. So knowing what our heat profile is that we want, properly prepared raw material, and managing the airflow and the fuel rates to deliver that heat as we want it. And the danger, just like in baking a cake or a pizza, the danger is that if you overcook or undercook, your product is not very appetizing, in our case for the construction industry. So very important to get the heat where we need it, and obviously combustion requires flow.
Brilliant. JP, from a process engineer's perspective, where are the operational challenges when tertiary air or downcomer flows are not well understood or controlled?
Thank you for that question, Ravi. So, of course, when those two flows are not well understood or controlled, first we have to realize that an unbalanced tertiary airflow leads to improper air-fuel ratio in both the kiln and the calciner. As you know, in the literature, we should have, let's say, 15 to 17% of the draft from the ID fan passing through the tertiary air duct. So to be sure that we have that good ratio to keep the balance in our, we need a measurement of the flow. Most operators, sometimes they rely mostly on the pressure of the draft in the duct, which could fluctuate because of turbulence. It's better to get the flow, actually. And if you don't control and understood very well those two flows, that could result, of course, in incomplete combustion. You will have more CO level, for instance. You could passing over 100 ppm at the kiln inlet or at the calciner. And of course, we'll maybe burn more fuel. As John said, we could cook a bit too much the raw meal, the hot meal at that stage, and spending money for wasting our money actually on energy for no good reason. And of course, if the downcomer gas flow increase, that could create more CO2 rich and oxygen lean gas that will enter the calciner. That's the big main issue. So not understanding and controlling the tertiary airflow and the downcomer flow, that could create problems of energy management and of course creating gas like CO and oxide of nitrogen oxide. That's it. Thanks.
Thank you, JP. It's good to have with us someone who is every day working at a cement plant. I have a follow-up question, please. What symptoms would operators typically see in the control room?
Yes, thank you for that question, Xavier. One of the first symptoms the controller will see is, of course, an increase of CO at the calciner, but also at the kiln inlet. And potentially, of course, both could, it's like an addition. You could have that at the stack. So operators will also see an increase. This is a very special case that we observe at the plant. So if you have, for instance, a kiln inlet buildup due to the alkali condensation at the kiln inlet, that will block a bit the draft at the kiln inlet, so that will reduce the flow. And if you are able to measure the flow at the tertiary air duct, you will see an increase of the speed or the flow at the duct. And that will be instant. And that will be a much more reliable measurement than just relying on pressure of the draft to know that a buildup is coming. You could even monitor the buildup at the kiln inlet. And of course, the other thing is that this is typically associated with poor combustion, of course, in the calciner. So that's it, exactly.
Thanks for that insight, JP. Let's move on to the next topic, which is around tertiary air and combustion controls. And my question is to Matthias. When you perform process audits, as you have very successfully around the world, how often do you encounter combustion problems that are ultimately related to airflow imbalance rather than burner design or fuel quality?
Very interesting question, Ravi. Well, we all know that the airflow through the burner shapes the flame and makes the combustion. But unfortunately, it contributes only to around 10% of the air which is required for the combustion, and thus it delivers not more than 10% of the oxygen which is required for the combustion. But the flame shape and the flame intensity directly affect clinker quality and kiln shell temperature. While the airflow or the airflow imbalance between tertiary air and secondary air, it impacts factors like energy consumption, coating formation, which comes quite lately, or CO emissions, which you can suppress by just adding more air. And these are more related to long-term efficiency parameters, and they are not immediate troublemakers like flame shape or primary air related issues. And that is why most of the operators, or let's say that's probably wrong, but some of the operators, they primarily focus on the control of the primary air because they control the flame with it, and they somehow rarely take care of the split between tertiary air and secondary air. So from my perspective, and that is the experience that I have from many plant visits I have done so far, that an tilted or unknown air split is one of the major hidden efficiency and performance limiters. And this is happening in quite many cement plants. People are trying to overcome this issue that they cannot see the airflow rates by measuring the kiln inlet oxygen or the preheater exhaust oxygen. But unfortunately, the kiln inlet oxygen measurement is somehow quite unreliable or requires a lot of maintenance because of the dust and the temperature impact in the kiln inlet chamber. And for that reason, the probe fails quite often. And in, unfortunately, many places I've been, it is even no longer in operation and it is dismantled because of this problem. On the other way, if you look at the preheater exhaust oxygen, this is distorted by the TOC combustion of the raw material and, of course, the false air ingress in the tower. And so you can measure it, but it doesn't give you the direct information on the airflows because it's already quite far away and something is happening in between. So, in fact, many of the plants, they are running almost or even fully blind with regard to their air split. And they don't know the actual oxygen supply to the kiln and the calciner. So they are not at all operated optimally efficient. And in particular, if you in your plant, you are operating a pre-combustion chamber or a separate line calciner where the combustion happens already in the back end of the tertiary air duct, this issue becomes even more severe, and the knowledge on an accurate tertiary airflow measurement is even more crucial than an inline calciner system.
Matthias, according to your experience, what are some of the hidden costs of poor airflow distribution?
Yeah, they are manifold. They are manifold. So if your air is not well distributed between tertiary, or let's say calciner and kiln, it finally increases your overall energy consumption or energy demand because you have more air in the kiln than you want, for instance, or your combustion is inefficient in another place, in another spot. And that in the end requires more energy overall. In addition to that, people, if you have an inefficient combustion, you will face some CO spikes, and people typically try to overcome those spikes by adding more air. So your exhaust gas flow rate or specific exhaust gas flow rate will increase, which is easy to understand, will increase your ID fan power and the electrical energy consumption. But it also comes along with higher fuel consumption. In addition to that, the combustion becomes unstable, and even the pneumatic conditions may be unstable in the process under these poor conditions and unknown airflow rates. And that forces many plants to reduce the production, and this is definitely then affecting the plant performance and the cost efficiency of the plant.
Excellent, excellent. So in recent years, as many of you are aware, many plants have been focusing heavily on alternative fuels and fuel optimization. So Xavier, given your background with fuels and combustion, could you provide a perspective on how important is airflow measurement in ensuring those fuel strategies deliver results?
Yes, Ravi. So, of course, the objective to increase production and decrease cost. So cement plants need really first to achieve a very stable operation. This is key. But alternative fuels are part of the decarbonation and often part of this cost reduction, especially if the CO2 value or cost, depending on how you see it, is part of the equation. But alternative fuel brings a lot of new variables. And to control those variations and then optimize those process control loops, airflow, gas, continuous and reliable flow measurement is key, it's essentials. These days, plants can't just rely on pressures and temperature. One example would be the Downcomer, where traditionally the measured oxygen would be the set point. But this is also not optimal. Airflow should be the set point with a correction in a cascaded control loop. So the highly dynamic flow signal, because it's refreshed every second, takes care of the short-term process variable to stabilize the ID fan. And the O2 analyzer, which is much slower in its response, provides longer-term adjustment. And thus, you eliminate systemic process noise and you avoid a potential slipping of the pyroprocessing into a transient state.
Very interesting, Xavier. So yeah, I'm sure we also discussed this a few months ago at the IEEE, but how would you rank the need for airflow measurement compared to all the other sensors or all the other measurements which are available? Because many people say more than 1,000 sensors exist, and which should I have at first, which is the most needed, yes? So how you would rank this? Thank you.
Yes, well, these are discussions, yes, during those conferences, but also during plant visits that I do on a regular basis. And I speak mostly these days to North America and the US, but many plants don't really have a reliable kiln inlet gas analyzer, nor do they have any frequent free-line measurement. And this would be the two absolutely critical data to optimize and control the pyroprocessing. So although continuous airflow measurements are not substitute for those, they would come in addition, but since they are inexpensive, easy to implement, continuous with a refreshment of every second, and with almost no maintenance, they are very valuable and should be implemented until plants can also look into those kiln inlet gas analyzer and free line online.
Thank you, Xavier. So let's move on to the next topic, which is kiln stability and pyroprocess optimization. And we have a cement operator and expert with us, Jean-Philippe. So, JP, when you think about kiln stability, what are the most important process variables operators should be paying attention to?
Thank you again for that question, Ravi. First of all, I like to say that in a cement plant, everything is linked to each other. So, for instance, we could focus on the kiln, but the preheater, the tertiary air duct, the flow, the pressure, temperature, everything is linked. And for instance, for the kiln inlet itself, the temperature, of course, of the kiln is a very important variable for the operator to know, but also the cyclone temperature to see if there is a good heat balance through the preheater and through the cyclones and the calciner temperature. So that will reflect the heat balance and also the combustion stability in the entire system. So if you have a healthy, for instance, preheater, you have more chance to have also a healthy kiln. It's not a guarantee, but a good start, let's say. So of course you have to follow, like everybody does that. Now it's the oxygen level, the CO, and the nitrogen oxide level that will indicate, of course, the combustion efficiency and the air-fuel balance. And of course, the nitrogen oxide will also be a level of a good indicator of the temperature of the core of the flame at the burner. To reduce the NOx emission, you will have to reduce that core temperature of the flame. The draft pressure, of course, it's mostly the most used variable to judge about the overall system balance a bit everywhere at the preheater and at the kill inlet and at the TAD. But I would like to say that if you are able to measure the flow at the preheater, close to your ID fan, and at the tertiary air duct, you will have a more, let's say, a more reliable picture about the heat balance and where the flow is actually going. For instance, you could see that you're lacking oxygen at the preheater because you're focusing too much on the kiln, for instance. So, and of course, you have also the feed rate versus the fuel rate. And of course, we should not forget the kiln shell temperature that you follow with the scanner, for instance, which is a good indicator of the coating issue, build-ups inside of the kiln, and potential refractory loss inside of it.
So,
Very good.
Jean-Philippe, you've mentioned quite a few different instrument measurements here. How would you rank them? What would be most important in your mind?
Thank you, John, for that question. First of all, if I have to rank them, I will rank the flow first, and the draft of the static pressure second. Because why I'm making that claim is there is some, in the literature, you could say that a static pressure, at some place where you will install those pressure transmitter, you could have a lot of turbulence, for instance, and those values could vary a lot. And if you are able to measure the gas flow, you will see that the flow will stay constant with, for instance, for a constant opening of the damper at the TAD. And you will see that your draft static pressure will vary, let's say from 80 millimeter water column to, let's say, 60. So there is a lot of up and downs, but the flow will stay constant. So that's why I'm judging the gas flow first and the static pressure second. And if maybe temperature might be the first one. After that, gas flow and the static pressure. That's it.
Excellent, excellent. And this is a great time to pivot to the role of CFD modeling and AI-driven optimization. Matthias, you work extensively with CFD modeling and AI-driven optimization. How does reliable gas flow data improve the effectiveness of these digital tools?
Well, just to explain first, the CFD model, for those who is not familiar with it, is a purely physical and chemical model. So it is converting input into an output, just following general physical and chemical laws. And it's easy to understand that models always rely on data quality. And that holds for both, for physical as well as for AI models. While the physical models, they require even correct data as absolute numbers because they are converting these absolute numbers into an absolute output, so into direct information on the numbers. And if you put something wrong in, I guess you get something wrong out. AI models, it's a bit different. They are not so much dependent on absolutely correct numbers in measurements, but AI requires quite stable information which shall not drift and which is continuously available in a non-interrupted way. And it shall be able to show the right trends. So in case of an AI model, if you have data from measurements where the sensor is interrupted or the data delivery is interrupted or the sensor drifted, then you immediately degrade the performance of this model. So, in fact, the universal principle for modeling is also to be applicable here, which says rubbish in, rubbish out.
Matthias, we often work together and we discuss those topics at length. Can AI compensate for poor process measurements?
Generally said, yes, it can compensate for some weak measurements or some interrupted measurements. If this AI is able to reconstruct missing information in general or missing information for a while if it is interrupted. And there's also the possibility to build AI-based soft sensors that can provide virtual measurements from some internal variables that you cannot measure directly online. But in particular for the airflows, because of a lot of noise in the process and in particular in the fuels, if you're applying alternative fuels, then an AI-based prediction of flow rates, of airflow rates, which is purely based on AI sensors, will most probably not work from my point of view. In fact, it is even vice versa, I would say, because some measurements are essential anchors for an AI-based control. And to my opinion, the gas flow measurement is one of those essential anchors to provide a stable and reliable AI control system.
Mm-hmm. Excellent. So, John, fans are among the largest energy consumers in the in cement plants. How often do you see fans operating away from their optimal efficiency?
The short answer, all the time. But we often see the large fans, the preheater ID fan, the vertical raw mill fan, the main baghouse fan, and the cooler vent fan. Those are the four that we'll always measure in an energy audit. And when we look at gas flow, if you look at what is the fan power requirement, the power requirement is the volume times the pressure times a constant divided by the efficiency. And we know that the pressure increases as the volume increases. So we can see that the volume is the most important factor in fan power. So, and if we know the volume, we know the pressure, then we can easily calculate what the efficiency is. And that can be done online or over time periods. But when we measure it in the plant, we're usually finding that they're off by about 10% or more from what the original fan curves say. So the fan, knowing the fan flow, you can estimate the efficiency or calculate the efficiency very quickly. And from the efficiency, you can start to determine what's causing the inefficiency and improve that situation.
Excellent. And Xavier, do you have anything to add to that in terms of, are you seeing any increased interest in measurement projects, especially driven by energy savings?
Well, yes. I mean, talking about the US, which is my focus, even it's a country that has always enjoyed relatively cheap electricity and fossil fuels, cost control is becoming more and more prevalent for the plants here. And when you integrate in a control room, in a control loop, either as a set point or correction to that set point, the continuous air or flue gas flow measurements do enable the reductions in ID fan power consumptions. Or if you look at another part of the plant, it allows the mill's output to increase while keeping the same quality, fineness, for instance, by optimizing the airflow through those mills. That's two examples. The third one would be measuring the airflow at the cooler vent, which helps or which is necessary to do a good calculation of the cooler mass and heat balance. And as we know, cooler is where all the combustion air for the pyroprocessing is generated. So that will enable a better control of the cooler fans, which flow is difficult to measure, as well as the important point, which is the kiln hood draft.
All right. So let's move on to another very vast subject, which is NOx reduction, and we could have an entire webinar on that, on environmental compliance. But very briefly, Matthias, could you touch upon whether, since NOx emissions continue to be a major challenge for many cement producers, how does airflow control contribute to NOx reduction strategies?
You're right, Ravi. This is really a complex question, and it's hard to address it in short words. But let's say it like this: the majority of the NOx that is produced in a cement plant, and this is especially the thermal NOx, is produced in the main burner. It's not produced in the calciner. So if we have excessive air in the kiln, then we need a higher flame temperature, and that promotes NOx formation, higher NOx formation in the kiln. So for an effective NOx control, I'm not speaking about destroying the NOx by applying SNCR, but a NOx production control that requires a proper know-how of the real combustion conditions inside the kiln. Instead, the calciner can contribute to the reduction of NOx because if we are implementing low oxygen zones in the lower section of the calciner, which are called typically the low NOx area, then we can reduce the NOxes under the absence of oxygen. And if we want to make efficiently use of exactly first the control of the NOx production in the kiln, and secondly the NOx reduction in the calciner, it is very important to keep our air split under control at the point where it is designed for. So the air split, to answer your question shortly, directly influences the NOx formation and the NOx reduction in the calciner.
Excellent. So that takes us to a rapid fire round, and we have a few minutes for that. And since we would like to take some audience questions, I would request each of the panelists to keep their answers brief, preferably within 30 seconds. So let me start with the first question addressed to John. What is the single most underutilized opportunity in cement plant optimization? If you could provide us with a brief answer, that would be great. John? Perhaps he's on mute, so we will get back to him when he's.
Sorry about that. I was still on mute. Sorry. The most important thing, underused opportunity right now for cement production is the use of SCMs, which require a highly reactive clinker. To make a highly reactive clinker, we need to master the combustion. We talked about that. So in the combustion operation, getting to 100% alternative fuel use and hopefully to a very high percentage of biogenic fuel use is the best opportunity we have right now.
Excellent. To Jean-Philippe, what is one process variable operators often underestimate?
Yeah, to give you a quick answer, Ravi, on that one, it's simply the draft flow. Draft flow generated by the preheater ID fan is very critical. Too many operators, they rely on the draft pressure of that fan, which can be misleading. So that's my short answer a bit. Everywhere at the preheater, it's better to rely on the flow measurement than static pressure. So that's a bit what, that's it.
Excellent. Matthias, what is one misconception about pyro process optimization?
Well, operators or process engineers often have to treat symptoms that they're seeing in the daily operation. And they have to do it in time shortage and immediately, and they call it optimization if they apply some quick fixes that appear the problem to be, or let the problem to be solved, but they never eliminated the underlying problem. And then we see that people do one quick fix after the other, and we get a chain of such measures, which gradually pushes the process away from its original optimum. And the plant is always ending up in an operation mode, which we call the survival mode. So the people are constantly reacting instead of controlling the process. And honestly, a proper root cause identification would unlock significant savings and restore stable and efficient operation, in my opinion.
Excellent. And Xavier, what is one investment every cement plant should evaluate?
Well, I'll do a quick self-promotion here. At the upcoming East Coast Cement Conference in October, I shall present on low-hanging fruits project with fast payback. That will go from leakless kiln seals to replacement of screw pumps by rotary feeders to how advanced CFD modeling helps plant debottle their operations. But part of this presentation will be on how adding continuous, reliable air flue gas flow measurement throughout the cement plant is both the lowest total project cost and also the fastest return on investment.
Excellent. And finally, Alexandra, briefly, what is one thing plants would do differently if they had to perfect flow visibility tomorrow?
Okay, thank you. So to answer this question, I have to tell you an emotional story. So what is getting me often said is when I see a plant having our PROMECON reliable gas flow meter, which is drift-free, and then is not utilizing out of it, not implementing it to a DCS or only showing a value, but not using it for some fan optimization or so on. So this would be the first step. And then something funny for the audience, patience. So when you discuss with your plant managers or the corporate level, a 3-month goal needs 3 months of data observation and at least 1 month to check. So if you implement such equipment and you will be asked after 1 week if now everything is fine, the answer is very easy. Yeah? So if you have all these KPIs and so on, you need patience. And like Jean-Philippe introduced in the beginning, all of them are linked: gas flow, temperature, alternative fuel combustion. So give the system some time, let the educated people monitor the process and then recheck it and see what are the benefits. Can you see some optimizations during the campaign? Is there some refractory via visible what you was not aware without the equipment, such topics? So patience.
All right.
Thank you.
That's great. So that concludes our rapid fire round. We will now take questions from the audience. If we are unable to answer your question or address your question during today's session, please be assured that we will follow up with you by email. So let me start with the first question, and this is to Jean-Philippe. Where is the best location to measure tertiary airflow?
Yes, thank you, Ravi, for the question. To keep things short on that, you should avoid a place where dust accumulate underneath the probes. So because if you have those, usually a flow meter, the instrument will measure a speed. After that, the flow itself will be a calculation, of course. But if you have accumulation of dust, you know that at that very location where you plan to install the probes, the sensors, you have to avoid that place. For instance, also a place where you have turbulence close to the damper of the TAD, for instance, it's not a good location. So a place where you could have a small slope where you are sure that no dust accumulation happen at that depth, that will be perfect. So that's my advice.
Excellent. The next question is, how often should flow measurement systems be calibrated? And perhaps, Xavier, you can take this.
Yes, of course, that depends on the type of flow measurements, but unlike traditional flow meters that rely on DP or thermal cooling, the triboelectric system, which is the basis for measuring the velocity, as JP said, and the flow, it is important only to know about the dust loading and the air velocity, which will result into adjusting the amplification of the signals, but there is no calibration necessary per se.
Excellent. There is a AI-related question, and perhaps I can address this to Matthias. How can AI systems help to save fuel? The question is, if we install a PROMECON flow meter, the questioner is asking how can that potentially help save fuel? Perhaps Matthias and or Alexandra can address this.
Yeah, Matthias, I take it first. So in general, the measurement does not have any AI system. So the measurement itself, it just serves for any AI system. But it delivers, as I said before, it delivers a very valuable information to the AI system, which is hard to identify. And once we have this information, the AI system is able to run the plant much closer to its optimum than it was probably done manually without having this information available. And by being more on the optimum and having the air split close to the optimum, of course, we can save a lot of energy. This is the typical potential that we know.
Very good. Very good. The next question is from a cement plant, and perhaps I can address this to Alexandra. How does PROMECON handle gas flow measurement under high dust environment and temperature conditions in a cement plant?
Yes, thank you. So the PROMECON device is relying to the triboelectric measurement principle, which is a vector measurement, and where all the other equipments struggle with dust, or our US American colleagues like to say, dust is our friend. So dust is the tracer which we measure near antenna 1 and antenna 2. This is something I can explain later in a follow-up session. But we can measure up to 1000 degrees Celsius, and like in the case of Jean-Philippe Gravel with his tertiary air duct, we also have an optical device which works up to 1500 degrees. The same system is used for electrical arc furnace off gas in steel melt shops, and if a device survives in a steel melt shop, it will also survive for long years in a cement mill. I hope this answered it in a nutshell.
Yes, that's great. That's great. So we are approaching a hard stop, so there's probably time for one more question, and I'll direct this at Alexa again, following which, Alexa, you can perhaps combine it with your closing remarks as well. So the question, again from a cement plant, is which gas flow measurement technologies are most widely implemented by PROMECON in cement plants? If you could briefly answer that and then also provide your closing remarks, that would be great.
Okay, thank you. So yes, we have two different principles for cement plants and some others for power and steel mills. this is, like all the other questions, something we can follow up in ongoing sessions, and I'm very proud that PROMECON is hosting this event together with an excellent panel today. I'm sure we will have to have such an event even more to bring some value to all the cement process people and share experiences. So gas flow is a often overlooked topic by different measurement principles. This is something I can cover later in a more detailed answer, because this is more than 5 minutes explanations. But yes, so thank you for all your time, and please remind that if you are thinking of artificial intelligence, the first step is data clearance, data transparency, checking the data, and please slow down to speed up. Be patient, check your process, evaluate where you would have the best benefit of a gas flow meter, maybe in a vertical raw mill, maybe it's your downcomer, maybe it's a tertiary air duct, and then we can discuss where there is a real value for your plant to finish John Kline's very excellent initiative to decarbonize our industry by having energy efficiency first and carbon capture second. Thank you.
Thank you, Alexa, for that closing remarks. So we've reached a hard stop, and I'd like to thank the audience for their patience and their attendance. We had an excellent turnout, and I'd like to thank Alexa, Xavier, JP, Matthias, and John for sharing their expertise today, and for all of you, once again, for joining us. If you have any questions, please feel free to reach out to the PROMECON team or any of our panelists following today's session. This webinar was produced and marketed by Webcast Experts, a division of Krishnan and Associates. Please stay tuned for any upcoming broadcasts covering a range of topics impacting the energy, infrastructure, and manufacturing industries. These events thrive on audience participation. If you found today's broadcast valuable, please feel free to invite your colleagues and share the link through your social media channels. The recording link will remain active for the near future. Thank you again, and have a wonderful day.